Well, that concludes episode 2. I hope you enjoyed that one. And now the grand finale. I saved a little bit heavier beer for that one because doing all these at once gets a little bit to your head. So with that said, let's go on to episode 3 on VFD drive installation considerations. So our third and final episode of VFD installation considerations is episode 3, where we're going to discuss the output side. We'll talk about VFD cabling considerations, output filtering options, VFD rated motors, and again, most of this can be found in the drive's PWM installation guide. So NFPA 79 2018 section 4428 basically states that VFD or servo output cables need to meet the NFPA 79 2018 standards, which means it needs to be flexible motor cable marked with XPLE or any of these above designations. But look for the fact that it meets the 218 standard. So when you look at VFD cable, there's a couple configurations. One is 3 conductors and a ground. And one is 3 conductors and 3 separate grounds split out and wrapped around all 3 phases. These are twisted in just the making of a cable, but this is the overall best. And Rockwell is good with this design, 200 horsepower and down. Over 200 horsepower, they like to see the 3 individual grounds. Now, this way I would prefer all of them you could get, that's the best, but either one is acceptable. So you have also the PVC jacketed type, where you have a foil shield and a braided shield, and there's a drain wire for connecting that to the shielding. Or you have the armor shielded, which has basically a flexible enclosed metal shielding like a conduit almost around it for added protection to the cable. So if we remember back in episode 1, we had a conduit that couldn't touch ground, and a lot of your high frequency noise would run along that because high frequency noise runs on the edge of most conductors and not through the heart. So when we add the shielding, that eliminates that path with the conduit. And now we're running from the shield, and we're bringing the shield back to our grounding. We're also grounding the shield at the motor end. If most of you are familiar with single signal wire, you only ground it at the source. But because we're trying to get that high frequency noise, which it's going to seek its path back to the drive, giving it the least resistance path, now is why the shield is there. Now, the one thing which we'll see in the next slide, the idea is to get that shield all the way back. I've seen installations where they stop it at the motor disconnect if there's one out here, or something short of the conduit box in the motor. So if you do that, you've just spent a lot of money on shielded VFD cable, which is very expensive. You might as well not have put it in at all. And the same way on this end, you got to bring it all the way back to be the best capability and best performance. So one way is when you hit the enclosure, you use a special gland that has a grounding bond ring in it that wraps 360 degrees around the shield. And then when you scrape back the paint and the lock nut here, it makes contact with the enclosure. And you still run your shielding back, your conductors back to the PE on the drive as well. And make sure this enclosure is grounded to the ground bond in the cabinet. Now, if you don't have that grounding bushing, the next thing is to bring the shield exposed and solder it on and bring it back to the PE or the earth ground in the cabinet. Now here's another method. This is a spring clamp that you strip the cable back, the insulation, and it clamps, and there's different sizes of this, of course, and it clamps around, making contact 360 degrees around the shield. And then you bring that back to the bonding in the cabinet. So again, the preferred method is to try to make 360 degree connection as close as you can back to the PE. So we also want to look at cable lengths and the effects of a VFD. You got what they call standing wave phenomena. So the further the cable, usually the further the mismatch in impedance, and you'll get spikes out onto your motor and your cable, usually at least twice the DC bus. So on a 480 volt system, you're looking at around 750, so closer to 1500 volt spikes that could achieve out at your cable and at your motor. In the installation guide, in the appendix, we have each drive Allen Bradley offers listed. So in this case, we're looking at a 60 horsepower, and this here is your PWM carrier frequency, which you can set in the drive, either at 2 or 4 or higher, which would even be worse, but that's usually on our smaller drives. So if we look at a 1600 volt insulated or above rated cable, and they're saying you can go 600 feet without that being an issue. And 500 volt if it is. Now, if your motor insulation is less than that, of course, you see your distances become way shorter. Typically, your newer motors are going to be in this range or possibly this range. But there's a lot of older motors out there. And the best thing is to get a hold of your motor manufacturer and let him tell you what it's rated for. I've seen some that say they're rated at 2,500. I don't know if that's on the same spec as the MG code, but you can ask them. Then, if this isn't long enough, you could add a output reactor to the system in series with the output. So it's rated for the same current as your motor is. And we can get out to 1,200 or 750. There's also this thing called a dampening resistor. Rockwell doesn't offer a DVD filter, but this basically is what they use for that. It's a little more expensive than a DVD filter, but it'll allow you, again, to go out to 1,200 at both frequency ratings. So then, say you don't really care, the cable is heavy enough, it's VFD rated and everything. You could also look at this here. It's called a TFB2. It's what Rockwell sells as a motor terminator. You have to run it at 2 kHz. That's why the dot's there, because this thing would get hot. It's like an 8-inch cube that's rated NEMA 412. It has to be within 10 cable feet of the motor and paralleled in the conduit box. Now that will eliminate the spikes going to your motor, usually under 1,200 volts, I've seen. But it doesn't protect your cable at all. And also it sometimes, depending on the atmosphere and where this motor is located, this is not practical. When you get into the higher horsepowers, this is very economical because it's not current size rated. It's one size fits all versus your reactors and dampening systems have to be sized to the current. Also, Rockwell offers us a site where there's a web-based simulator. If you log on to this site, it's free. You put your email address and information, and you can actually do more accurate than just the chart that they show. So if we go, these are the different options you can do. You can do harmonics and everything else, voltage drops, but you also have, which we're talking about right now, is the reflective wave. So when you get onto this site, there's the things you'll have to fill in, like the drive type. There'll be a pull down selection. 755 works for 753 as well. They're the same. The 6 pulse, 480 volt input, normal duty or heavy duty, the horsepower rating gives you the current. That standard is 4 kHz on that one, but you could change it to 2 and see what it does. If you're going to have an output device, you select it here. Again, Rockwell doesn't sell a DVD filter, so that option's not here. So use the RWR to get an idea where that puts you. Or check with your DVDT supplier, because they've changed some of their ratings. Before, they used to be able to go like 3,000 feet. They're limiting that depending on the application. Now they're more critical than they used to be on those. You pick your wire, the gauge, the length, and your NEMA rating. I went with the 1,500 because I go, that should cover everything that's out there today and give me a little cushion. So once you do the simulation and you press that button, you wait. Sometimes you wait a minute. Sometimes I've waited 5 minutes for this to happen. But eventually unless it fails and you got to try it again in the actual process, this will pop up and it'll tell you whether that motor is going to handle that or not. In this case, it failed because we were over the 1488, not by much, but it was still above enough that would eventually break down that motor. So I did it again, and I put a 3% reactor in there this time, and it passed, and we're down to 1319. So if you look in that installation, PWM installation guide, it gives you a breakdown of what those different motors were that we had to select from. Again, we're typically looking in this area, and probably today, most of the newer motors are going to meet this. And that's MG1 part 31.40.4.2. And that's where we get the 1600 volt. Rockwell used to sell motors, but we no longer do, or they no longer do. So that's what this 1329 RL is in there. So that's no longer available from Rockwell, and they had other manufacturers build the motors for them. So you can just get a hold of somebody like Marathon, who has inverter rated motors for different applications. Not only are we looking at motor spikes, but sometimes the application where you need to go down the stall or everything or anything. So you have 1000, 2001, which are stall based motors without overheating. We're looking there. But right now we're just talking about the spike insulation. Marathon has the max guard. It meets the MG1 part 31, etc. for the 1600 volt. So besides using the transit, you look at the PWM guide, look at your installation guide, you got your technical guide, you got your drives, installation guides. And again, all this information for complete installation of your VFD can all be found on Rockwell Literature Library, and that's at www.ab.com. So that concludes episode 3. Now you're ready to install your VFD. Hope this was good information for you.
Well, that concludes episode 3. I hope you enjoyed them. And again, as always, if you need questions or more concerns, give Tri-State Supply a call and we can discuss it further. And again, with the supply chain shortages, you should think ahead about doing any projects. And as always, don't dilly-dally.